Hello, this is Tech, 11th of August 2011. What I'm going to do today is run a couple of tests on the latest version of the Muller Motor Driver software for zero fossil fuel. On one screen over here we have the Arduino version 0.022 IDE running the program. And over here on this screen we have a DSO showing two pulse streams. On the top in blue we have the input pulse stream going to the Arduino, and on the bottom half in red we have one of the two output or resultant pulse streams coming from the Arduino after processing the input pulse stream. At the moment on the IDE we can see that the dwell percentage is set to 50% of the input pulse period, and the dwell delay is set to 0% of the input pulse period. Just to confirm, I will now upload that code and we'll see over here the Arduino doing its job. It's currently receiving the software. Okay, let's take a few measurements. But before we do that, I just want to establish one or two things. The DSO is currently set to 200 microseconds per division, therefore showing from the left to the right edges of the screen 2 milliseconds. So roughly we're getting 1 pulse per millisecond. I'm just going to set it so that it's roughly a 50% duty cycle, and as I do that you'll notice that the output pulse characteristics are not affected by the duty cycle settings of the input pulses. Here we go. Here we are. This is because the calculations for the output pulses are based on leading edge to leading edge of the input pulses. So I'll set that roughly to about a 50% duty cycle, purely as an aid for the measurements I'm going to take in just a moment. Well, it's closest, damn it. Okay. First thing I'd like you to note is, whereas the input pulse starts here, incidentally I've got it set to trigger on the rising edge of channel A, which is this, at 4000 millivolts, because there's a slight amount of variance in this range, and to guarantee no jitter whatsoever on the display I've set it to that value. There's no pre-triggering taking place at the moment. Now we see, whereas the input pulse leading edge is here, on the output pulse it is here instead. This area here, the latency is measurable, and we'll do that right now. Let's see now. We can do that one of two ways: either measure it from the leading edge or from the trailing edge. Let's measure it from the leading edge, and we'll see roughly it is set at what? 77 microseconds. Now that 77 microseconds is something that needs to be borne in mind for this particular test, which is set at 0% delay. Now I'm going to set the delay to 75% of the input pulse period on the Arduino. So we'll just move that down to here on this screen. Alter that to 75 and then upload it, and we'll see the changes being reflected on this side here. Okay, so now we have the leading edge of the output pulse in this position. Now, seeing as I've just set it to 75% of the input pulse period, I would expect it to be around here. We set the X position at 750 microseconds, or close to it. That's close enough. We see that the latency manifests itself once more here. But what is this latency, given that we are at 75% of the input pulse period for the delay? Well, let's measure that and take it there, and we've gone from 77 microseconds to 35 microseconds. That is something that we need to account for as we develop the software further. A, to reduce that latency as much as possible, and or B, as we build any supporting circuitry around the software for external devices such as motor drivers. Okay, that test was for a 50% duty cycle. Let's do exactly the same thing, but now we'll set the delay back to 0% and the dwell to, well, for example, 25%. So we'll do that now. The delay goes back to 0 and the dwell is now 25, and we'll upload that. Arduino's busy once more. Okay, there we are. We have the leading edge of the output pulse once more starting here, and let's have a look if that's similar to how it was before. 79, 80 microseconds. Yeah, that looks about right to me. And we'll set the delay for this dwell setting back up to 75% of the input pulse period and upload that. Okay, once more we see that if we place the X cursor at about 750, we see that the leading edge on the output should be starting around here, but we have this latency. Let's measure the latency. The latency appears to be about 93 microseconds. So there's the two measured sets of latencies for the two different settings for the two sets of tests we've just run. So far, so good. Once more, with the current dwell percentage set at 25%, you see it's not sensitive to the actual duty cycle settings of the input pulses, because, as I said earlier, we're measuring leading edge to leading edge. So now it's a matter of setting it back down to roughly about 50%. Again, it's not a requirement for the following test, but it's just that I prefer things to be evenly balanced. It's just the way that I prefer to work. I'll set the dwell percentage to 50% once more, and I will also set the delay back down to 0% and upload that. While we wait for that, I'll just say that the following test is to see what the bandwidth capabilities of the software are. I'll just remove these cursors for now. Delete. Where's the delete key? There it is. Delete that one and delete that one. And what we'll do is we'll increase the frequency of the input pulses, or the input pulse stream, to see how stable the output pulses are as the frequency increases. Remember that at the moment it was set to roughly about 1 kilohertz, 1 pulse per millisecond. If we take this up now to, let's see, we're roughly 1, 2, 3, 4, 5 pulses every 2 milliseconds. 1, 2, 3, 4, 5, 6, 7 pulses. 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 pulses. I think this was tested last properly at about 8 pulses every 2 milliseconds, giving us 4 pulses every millisecond, giving us 4 kilohertz. Well, that's close enough. Now, as we alter the duty cycle at this input frequency, we can study the stability of the output pulses. We see there is some sensitivity there at this frequency, but overall I think we're looking at quite a stable output pulse stream. That's good. Now we'll set the delay on the output pulses back up to 75%, maintaining the frequency of the input pulses, and upload that to the Arduino, and we'll note the stability on the scope. Once more, it looks like we've got a very stable output, and I'd like to see how that stability is affected as the input frequency is reduced. We can see that by doing this, the software, or the Arduino running this software, should be able to follow the acceleration profiles of the motor quite well. I think some more work might need to be done regarding sensitivity, possibly adding some sort of buffering mechanism. The facilities to control the dwell and delay via potentiometers is still in place, but it's very sensitive, and I feel will require supporting circuitry before the actual pin on the Arduino sees the voltage change. Well, so far so good. I think that's a good result. This is ready to upload to Zero Fossil Fuel.